We're going to take a look at Chapter 11, Energy and Thermal Processes. Up on the screen, you can see these are the things that you need to know in this particular chapter and section. We're going to definitely be focusing on basically how we measure the internal energy of a substance, the specific heat of a substance, and how calorimetry allows us to measure how heat is changing using the zeroth law of thermodynamics. You're going to need to be able to do the following things. You're going to need to calculate the energy needed to change some temperature of specific substances, solve conservation of energy equations, set up and solve calorimetry equations, and calculate thermal energy flow through different media. First, internal energy. Energy has two forms. It's got potential and it's got kinetic. The internal energy of a substance is really just the sum of these particular energies. So there's kinetic energy in terms of vibrational, rotational, translational motion because the particles of objects are moving. And then there's also bonds between those particles, which forms a kind of potential energy. So internal potential energy, we have some examples of solids, liquids, and gases. Then in a solid, all the molecules are going to be rigidly packed together. In liquids, they're going to be able to flow a little bit more. And in gases, they're all bouncing around whatever container they happen to be in. But even in solids, they are still moving. They're vibrating, they're wiggling, they're doing all sorts of things. And therefore, they're going to have some kinetic energy. And at higher temperatures, they're going to wiggle more and eventually be able to flow. That's when they turn into liquids. And if we keep adding temperature, keep adding heat energy, they will eventually turn into gases. And they have so much energy that they can bounce all around whatever container they happen to be in. When we're measuring heat, the unit of heat is energy. It's measurement of energy, and we're going to still measure that in joules, just like we did in Physics 1, where we measure potential energy and kinetic energy in joules. That's the case when we're measuring heat energy as well. When we're talking about like English units, BTUs, can be used, and also the calorie, which, again, a unit of food energy, which is very common on your food packaging. But a food calorie is actually 1 kilocalorie. Specific heat. Every substance takes a particular amount of energy to get their temperature to increase or decrease by particular amounts. Water, for example, has a rather high specific heat, whereas plenty of metals have a much lower specific heat. It's much easier to heat them up or cool them down. So this is different for every substance. How much heat does it take to change the temperature of something? Well, we have an equation for that. Q is the amount of heat that we have to add to or take away from the item in order to heat it up or cool it down. M is the mass of the object. C is the specific heat, which again is going to be different for every object. And T is the change in temperature as a result of adding or taking away that heat energy. We can use that knowledge in something called calorimetry, where we can measure the specific heat of different items. And now we learned about the zeroth law of thermodynamics, where if we take a hot thing and we take a cold thing, we put them together, eventually the heat energy from the warmer thing is going to transfer to the colder thing until they reach the same temperature. And calorimetry is just doing that. So we can take a substance that we might not know the specific heat of, and we can submerge it in water. That is at a different temperature. Now, we need to know how much water there is. We need to know what the temperature of that water is. But ultimately, all the energy gained or lost by one substance is going to be given or taken away from the second substance. Because ultimately, again, heat is energy, and energy cannot be created nor destroyed. So calorimetry is really just conservation of energy, but we focus it specifically on heat energy. Now, matter can change phases. Most commonly, or most thing that you're probably most familiar with would be water, because water can freeze, become a solid, and it's ice. Water can be a liquid and be water, and we can boil it and turn it into water vapor, which is a gas. And typically most substances can exist in all three different phases at various temperatures. Now, the amount of energy that it takes to change something from a solid to a liquid, or a liquid to a gas, or back, gas to liquid, liquid to solid, we call that latent heat. So latent heat of fusion, which is LF, is going to be the amount of energy required to change a substance from a solid to a liquid, or back from a liquid to a solid. It takes the exact same amount of energy to transform a particular mass of a substance from solid to liquid, or from liquid to solid. You either have to put energy into it, changing it from a solid to a liquid, or take that energy back out, changing it back from a liquid to a solid. And then the latent heat of vaporization is the amount of energy necessary to transform a certain amount of a liquid into a gas, or take that gas and condense it back down into a liquid. We have different ways of giving heat energy. There's conduction, convection, and radiation. This picture shows all three, where conduction is if you grab the pan handle, you are touching it directly, and that would be conduction. Convection is the water boiling, and you're going to get a current basically in there where the higher temperature liquid is going to flow toward the top and the lower temperature is going to flow toward the bottom. That's a movement of a hot fluid. And then radiation is given by electromagnetic waves, which is why you might feel warm on your face when you stand out in the sun. We have thermal conductivity. Basically, energy is going to flow from the hotter place to the colder place. And we can calculate the rate at which that energy is going to flow using this following equation, where P is the rate of energy transfer. So again, we're talking about rate of energy transfer. That's power. So we're talking about, that's why we're using P there. So basically, it's the power of this energy flow is going to be equal to K, which is the thermal conductivity unique to the substance. So some substances will allow heat to flow more easily than others. A is the cross-sectional area. So the bigger the cross-sectional area, the more area there is for heat to flow through the substance. L is the thickness. So if you have very thick walls in insulation, it's going to take a little bit longer for energy to flow through more insulation than less insulation. TH is the temperature of the hotter area, and TC is the temperature of the colder area. This is very common when you are engineering certain things that you want heat to flow through or that you don't want heat to flow through. Think of insulating your house or windows that are highly energy efficient. You don't want your air conditioning inside the house to leak, or basically the hot outside to leak into your cold house when you have air conditioning, or in this wintertime when you have a hot inside of your house and it's being heated, you don't want that heat to travel through the window to the outside. So factors affecting the heat rate, we just talked about these. The temperature difference, the larger the difference in temperature, the larger your rate of heat transfer will be. The material itself, so some materials carry heat better than others. The cross-sectional area, again, so if you're talking about windows, the larger the window, the more opportunity there is for heat to transfer. And L, how thick. Let's say, again, if we're talking windows, how thick are the panes of glass? Is there a vacuum or air space in between? So how thick are those things are also going to affect the heat transfer. So there's a slightly larger picture we can see. The hotter reservoir on the left, the energy transferring to the colder reservoir on the right. Again, this can be a factor when you're talking about insulating your house because different areas of the country, if you're just talking about this country, are going to have different needs in terms of insulation based off of the climate that they're in. So this picture that's on the right side here, you might be able to see it past my face, is from Energy Star, which does different ratings on things like heaters and air conditioners and insulation. And you can see these different R values, and R values have to do with the amount of insulation that you need. If you get into structural engineering, you're going to definitely be messing with your R values. And you can see an equation here which deals with the amount of energy transferred from your hotter area to your colder area, again, based off of area, change in temperature, and then the sum basically of your insulation. And you would just add up your different insulation types, and that would eventually get you your R value. We talked a little bit just a minute ago about the different ways to transfer heat. So convection, which happens in fluids. So when you're talking about changing ocean temperatures, or you're talking about the atmosphere, that's where you're really going to be talking about convection. And then we also have radiation. And in radiation, we have an equation for the amount of energy that an object can radiate. And the amount of energy, again, we're talking power because we're talking about rate of energy being dissipated or absorbed from a particular object. So P is the rate at which energy is radiated from a particular object. Then we have this funny little letter, which is the Stefan Boltzmann constant, which is given there 5.6696 times 10 to the negative eighth watts per meter squared Kelvin to the fourth power. A is the surface area of the object. E is the emissivity, which is a rating from 0 to 1. 0 would mean that it doesn't radiate anything, and 1 means it will radiate the maximum amount possible. For objects that have an emissivity of 1, they're called black body radiators, because if you saw them, they would radiate everything and they would appear black. And they would also, because they would also absorb all light, so they wouldn't reflect any of that. T is the temperature of the object. So notice that we have temperature to the fourth power. So the warmer the object is, it's going to radiate a lot more energy than when it's cooler, because again, you're talking the power is proportional to the temperature of the object to the fourth power, which is quite large. Now, objects don't just radiate energy, they also absorb energy. Now, for some objects, they might take in more than they radiate. That's if their surroundings are warmer. And if the surroundings are cooler, you would tend to radiate more than you would absorb. But we can calculate the net amount of energy gain or loss based again off of this equation. So the net amount of energy that an object either gains due to thermally or is going to lose thermally is given by this equation. Again, we have the Boltzmann constant, the total surface area of the object, the emissivity of the object, and then we have to take a difference of the temperatures to the fourth power. But we can use these equations when it comes to the radiation of energy to calculate things like the amount of energy that's being radiated from our sun. We can figure out the emissivity of it. We can know the surface area because it's just really kind of a big sphere. And if we know the temperature, we can figure out how much energy the sun is radiating any given second, which is kind of cool. So this is also very much used when we are talking about things like nuclear science and also astrophysics. And that's it for chapter 11.